Good morning, one and all. I am Dr. Ramya, swetha, Assistant Professor, Department of Civil Engineering from Institute of Aeronautical Engineering. Today, our topic is Castigliano's theorem. So, as per know about the analysis of structures, what are the various kinds of analysis we are choose for analyzing the structure based on the sum of the properties and identify which category of that particular structure, whether it is determinate structure, whether it is indeterminate structure, how many number of joints are involved, what kind of forces are there, what kind of loading conditions we are applying. These are all the parameters which we are going to understand in this analysis of structures. So as per the Castigliano's theorem, analyzing these structures in under various elements. So in this analysis of structures under degree of internal and external indeterminacies using Castigliano's theorem. So we have to resist these external forces, and from the what are the loading conditions we are applying. So based on that loading conditions, we are getting some internal forces developed gradually from 0 to their final value of and how much work we are going to done according to that. So to resist these external forces, the internal forces developed gradually from 0 to how much value we required from this for this work done. So the internal work done is stored as energy in the structure, and it helps the structure to spring back to its original shape. So it again comes back to its original shape and size whenever the external loads are removed. So such type of material of the structure is still within the elastic limit. We know within the elastic limit means whatever the external load we are provided for that external force, because of these internal forces, it gain its original shape. So before that, it is going to somewhere it deforms. So how much it deforms, and once we remove the external load, it comes again its original structure, original shape, or whatever the properties, geometric properties are regained. So such type is nothing but the elastic limit. So this internal work which is stored as energy is due to the straining of the material. So once we are straining that material, it has internally that energy. So that is nothing but the strain energy. So whenever it is without anything, there is no deformation, there is nothing, there is in such type of scenario, once we applied some load, so the element has its own energy. So that is nothing but the strain energy. So once we remove this load, it again its original shape. So it comes its back. So that is nothing but such the internal work which is stored as energy due to the straining of the material. So it is called the strain energy. So when equilibrium is reached, as per the well-known law of conservation of energy, the work done by the external forces must equal to the strain energy stored when the equilibrium is reached. So whenever we are talking about these equilibrium condition, so once we applied the external forces must equal to this strain energy. So according to this concept of energy balances utilized in structural analysis to develop a number of methods to find out the deflections of the structures. So here it deals with the following methods for finding the deflection of beams and frames. So those are strain energy or real work method, and virtual work or unit load method, and the other one is Castigliano's theorem. This Castigliano's theorem we understand whenever the equilibrium condition, it means how much external load we are applied, whatever the external load, the internal force, the energy, it is ready to regain its original shape once we remove this external load. Such type of strain energy is stored. So both are equal, must equal in this whenever the structure, the element which is reaches its equilibrium condition. So for this, understanding these deformations, how much development on the deflections and what kind of changes are there, how we are dealing with this for understanding this structure. So these, for this concept we have three different methods, that is the strain energy method, or real work method, strain energy method, virtual work method, or unit load method, and the third one is the Castigliano's theorem method or theorem. So these are the methods we have for understanding the concept of this energy balances. So in this Castigliano's theorem, Albert Castigliano published his work on the variation of strain energy system into two parts. He is the person who published this theorem in two parts. The one is, in this part 1 and part 2 of his work are often referred to as Castigliano's theorem 1 and 2 respectively. They are known as dou u by dou delta is equal to P. This is the theorem 1, part 1. Now dou u by dou P is equal to delta, that is part 2. These two are as referred as Castigliano's theorem 1 and 2 respectively. In this, what we talk about this dou u by dou pi and dou u by dou delta is equal to P. So here the u is nothing but the strain energy of the system, how much energy which is stored in that system. And P is the external loads applied at a point. So whenever we consider that is a point, I means, so it is nothing but the point. So external P is nothing but the external loads applied points, whenever it may apply. So external loads applied point. Delta is the deflection point. Delta is the deflection point. So the strain energy and virtual work principle play an important role in the derivation of the Castigliano's theorem. So these are the various parameters which we are going to understand this Castigliano's theorem. The one is U is strain energy, P is the external loads, delta is the deflection. These are the various parameters which are involved. Now the external work and strain energy, what is these external work and strain energy? So the deflection of joints and truss or points on a beam or shaft can be determined using the energy methods. So whenever the deflection joints and truss are points on a beam, deflection points on a beam or shaft can be determined. They are going to determine using these energy methods. Now, before developing any of these methods, however, we will first define the work caused by an external force. So, how much work is going to caused because of this external force, and couple movement and show how to express this work in terms of a body strain energy. So this is the, before developing all these methods, we have to understand this work in terms of how much that particular element strain energy. So the formulations can be presented here, and in the next section we will provide the basis for applying the work and energy methods. So here the work of a force. So consider, so whenever the load is like this, so in machines, a force does work when it undergoes a displacement dx. So in the same direction as the force, now the work done in scalar. So the due is nothing but the how much force, and the dx is nothing but the displacement. Here F is the force and x dx is the how much displacement because of the force. So now this u is nothing but the strain energy, how much work is going to done. So in between the 0 to delta, this deflection, so the total displacement is delta, how much deflection is happening in between 0 to, so this force and the displacement. So this is the work force, work of a force. Now to show how to apply this equation, we'll calculate the work done by an axial force applied to end of the which was shown in figure A. So in this, so we are applying. So in this, how the work done is shown in figure. As the magnitude of force is gradually increased, so from 0 to some limiting value, so force is equal to P. The final displacement of the end bar becomes delta, the deflection. So if the material behaves in a linear elastic manner, then the force will be directly proportional to the displacement, that is equal to force is equal to P by A into X. Now substitute into the equation and integrate from 0 to delta, what we get is equal to half into P delta. So like this, we are understanding what are the various elements involved in this. So now how this force is gradually applied to the bar and its magnitude builds from 0 to some value P, and consequently the work done is equal to the average force of the magnitude. So that is the P by 2 times of the total displacement. In the total displacement delta. So now we can represent this graphically as the light blue shaded area of the triangle which was shown in the figure. This is the 0 to this is which we shown in figure C. Like this, we are going to understand the consideration. Suppose, however, the P is already applied to the bar and that another force P bar is now applied, so that the end of the bar displayed further by the amount, that is delta, which was shown in figure B. So already it is deflected with P and some more another P bar is acting. So this is delta bar, and now so this is the previous one. Now what we are going to understand is that, so the work done P bar is equal to the grey shaded triangular area, but now the work done by P when the bar undergoes this displacement is strain energy is equal to P into delta bar. So this shaded area from here to here. So this is the P bar and here this is the delta. This much displacement is going to happen in the work force condition in the strain energy. So the work represents the dark blue shaded rectangular area which shown in the figure C. So now that in this case P does not change its magnitude, since the bar displacement delta bar is caused only because of this P external, whatever the extra applied, extra more. Already the load is P is applied, the displacement delta is happened. Now few more we are going to apply. So therefore work here is simply the force magnitude P times the displacement delta. Now strain energy. When loads are applied to a body, they will deform the material. So once we are applying the load, they will deform of the material provided no energy is lost in the form of heat. The external work done by the loads will be converted into internal work, that is nothing but the strain energy. So whenever we are applying loads to a body, they will deform the material. So whenever provided no energy lost in the form of heat, the external work done by the loads will converted into the internal work. that is nothing but the strain energy. So this energy, which is always positive and is stored in the body and is caused by the action of either normal or shear stresses. So this action either normal or shear stresses. So like this we understand this strain energy. So how we are determining the bending strain energy in a region. So consider from A to C, this is the A and this is B, this is C. Here the load is applied, this is the hinged support and this is roller support are there. From A to B the length is L, from B to C is the length is L. So here the load P is applied. So whenever a free body diagram of the beam which is shown in figure B, so we will see. So this is determine the bending strain energy in a region of AB, and whenever the load is applied at point C, the segment is we are going to consider in this the velocity is constant, EA is constant, that EA is constant. A support is hinge support, B1 is the roller, and load applied at point load, the two at C, which was as shown in figure. For this we have to draw the free body diagram of a beam, and to obtain the answer we can express the internal movement in the terms of any of the indicated of 3 x coordinates. So each of these solutions will now consider. So first we draw the free body diagram. So that is, this is the load condition. That means what we are considering, so some value. So this is the free body diagram and this is the B, and this here it is the load is applied. Now this is the, from section we consider x1, from here this is x1, from here to here this is equal to x2, and from here to here this is equal to x3. This is A and this is B and this is C. Now so this is the P, this is down, so both this means it is equal to 2P. Now and again we consider till x1. So x1 is equal to like this. From free body diagram of the section C, from the based on this again. So now the movement with respect to NA is equal to 0. Now M1 plus Px1 is equal to 0. Now M1 is equal to minus Px1 using the formula integral m square dx by 2EI. So finally P square L3 by 6EI is the thing what we get from this strain energy. From we consider x2 in between like this using the free body diagram of the D. So that is here this is V2, and from here to here that is x2, from this is the B, somewhere here A, and from here to here this is equal to P is there, here to here that is equal to L, this is equal to x2. Draw the free body diagram based on the movement conditions. So this M2 plus 2Px2 minus Px2 plus L. So here to here that is x2, from here to here that is x2 plus L is equal to 0. Finally M2 is equal to Px2 minus L. Using the strain energy formula, integration m square dx by 2EA, that is from 0 to L. Substitute, finally we will get P square L3 by 6EI. Now we are going to this x3 from L to this 2L. Draw the free body diagram for only this portion x3 minus L, and now final equation is this after done the calculation. So in this previous example indicate the strain energy for a beam can be found using any suitable x coordinate. and it is only necessary to integrate over the range of the coordinate where the internal energy is due to determined. So here the choice of x1 provides the simplest solution. So based on this Castigliono's theorem applied to trusses, since a truss member is only subjected to an axial load, the strain member for the given equation is nothing but the delta is equal to dou by dou p sigma L square L by 2 AE. So it is generally easier to perform the differentiation prior to the summation. Also L comma A comma and E are the constant for a given member, and therefore we can write delta is equal to sigma n dou n by dou p L by AE. These are the theorem which we are applied to these trusses. So here delta is the displacement of the truss. Displacement of the truss joint. P is external force. N is the internal axial force. Internal axial force member caused by the P, and L is the length of the member. A is the cross-sectional area of the member. E is the modulus of elasticity of the material. Modulus of elasticity of the material. So, what kind of procedure for this analysis we are going to follow? This external force, internal forces, and like this, what kind of procedure we follow for this? The following procedure provides method that may use to determine the displacement of any joint on a truss using this Castigliono's second theorem. So in the external force P, place a force P on a truss at the joint where the displacement is to be determined. This force is assumed to have a variable magnitude and should be directed along the line of action of the displacement. Coming to the internal forces N, so determine the force N in each member in terms of both the actual and the numerical loads whatever we are giving and these variable force P. So assume the tensile forces are positive and compressive forces are negative. So in internal forces, the compressive forces are negative. Compressive forces are negative and the tensile forces are positive. Tensile forces are positive. And find the respective partial derivative of the dou n by dou p for each member after n and dou n by dou p have been determined. Assign p its numerical value if it is actually replaced real force on the truss, otherwise set p equal to 0. So this Castigliono's second theorem, apply this Castigliono's second theorem to determine the desired displacement. So it is for the displacement point of view. So the desired displacement, it is important to retain the algebraic signs for corresponding values of n, and dou n by dou n is greater than the dou p when substituting these terms into the equation. So if is the resultant sum sigma n dou n by dou p L by AE is positive. So delta is in the same direction as P. If negative value results, delta is opposite of the P. So here in this particular case, delta and P same direction. In negative means both are in opposite. Those delta and P both are opposite direction. So like this we are going to understand this equation. So here determine the vertical displacement of a joint C of the steel stress which is shown in figure. So here the steel stress as shown in figure, and as per the here the hinge forces are there, and this is the diagram of the figure, and these are the supports which they consider, and this is the joint C, this is D, this is A, and this is B. This is from 2 meters, 2 meters, from here to here, this is 2 meters, and here the loading condition 100 kilonewton. Find out the vertical displacement of the joint at C. Now, external force P, a vertical P is applied to the truss at a joint C. Since this where the vertical displacement to be determined, which was shown in figure P. So now we are going to understand at D and various loads how we are consider for this in using this one at A and at P. So these are the things which we are going to understand from the figure C. Figure B from to C. So here we understand. So the internal forces N, the reactions at the truss supports A and D are calculated and the results are shown in figure B. Using the method of joints, the N forces in each member are determined, which are shown in figure C. For convenience, these results along with their partial derivatives are listed in the tabular column. So these are the values. Based on the Castigliano's theorem, second theorem we applied. Substitute the final value, the displacement, vertical displacement is 12.1. This is the procedure which we follow for identifying the vertical displacement as per the Castigliano's second theorem. So these are the sum of important references. They may give better knowledge about these Castigliano's second theorem, how we are analyzing the stresses based on the theorem. Thank you. We will see in our next class.
Like, share and subscribe. Hit the bell icon for more updates.